Okay, so we are starting. So today's webinar is going to be dedicated to fiber reinforced concrete modeling. It's about fiber reinforced concrete models that we are using in ATENA, and then also about our APIS FRC module that is actually automated module that is optimizing the material model for fiber reinforced concrete. I will just briefly go to contents that I will first introduce the material models for fiber reinforced concrete that we have in ATENA. Then I will introduce you to our optimization module, APIS FRC. I also will execute calculations, so you will see how the interface of the module looks like and how to navigate it. And at the end, we have time for some questions. So I guess most of you are familiar with our software that is used for nonlinear simulation of reinforced concrete structures. In general, the material model that we are using for concrete is very versatile, and it actually captures the behavior of concrete for its tensile response and also compression. In tension, we are using the whole model is fracture plastic model. So in tension, for tension response, it uses orthotropic smear cracks model with crack band and fracture energy. And for compression, we are using the plasticity based model. These are like the models for concrete, but we have also models for reinforcement and for the interaction of reinforcement and concretes. Therefore, we are able to capture the real behavior of reinforced concrete structures. Today, we are focused on fiber reinforced concrete. There are different types of fibers, especially when it comes to material. There might be like steel, polymer, or glass. But the main difference from the normal concrete is the strain softening part of the stress strain diagram. And this part of the concrete response for the tension, like when it comes to normal concrete, it might look like this, but for the fiber reinforced concrete, it might look like this. So we need to have specific models that are capturing this sort of behavior for the softening branch of the stress strain diagram. In general, maybe I will switch. Yeah, so you can see a little bit better where I'm showing. So in general, the stress strain diagram for fiber reinforced concrete is consisting of three parts. The first part is when there is no crack in the concrete yet, and it ends when the first crack is starting to develop. Then there is the second part that is called strain hardening. And during the strain hardening, there are multiple cracks that are developed. And it ends at the point where the maximum stressed post-crack is reached. And at this point, the last part, the third part of the stress strain diagram that is called strain softening is starting. And during the strain softening, actually one critical crack is localized, it's opening, and those other cracks that develop during the strain hardening, they are closing and unloading while the critical crack is opening. This sort of diagram is typical for high performance concrete, and actually the normal fiber, the standard fiber reinforced concrete has this sort of diagram without the strain hardening part. So in ATENA, we have 3 different material models that are they can be specifically used for FRC. However, only 2 of them are suitable to use it with our APIS module for the automatic optimization. So this last one is just mentioned here that you know that it exists, but I will not really introduce it properly because we are focusing on the optimization process with APIS module today. So we have 2 different material models. The first one is called cementitious 2 strain hardening concrete composites, and the second one is cementitious 2 user. The cementitious 2 strain hardening concrete composite is mainly developed for high performance concretes and ultra high performance concretes, and it has the tensile softening regime and shear retention factor that are modified. That was introduced by Kabele, and also he introduced the representative volume element that contains distributed multiple cracking and localized cracking that are visible on these pictures. And what is interesting about this material model that it actually counts with the fibers in opened cracks. It's called a shear bridging model that is assumed only in the strain hardening part in the multiple cracking regime, when actually the volume, the volumetric fraction of fibers that are in the concrete and the mechanical properties of fibers like shear modulus or Young's modulus and the diameter, those are assumed that they prevent the sliding of cracks when they are open, but they are captured with the fibers. Then there is the cementitious 2 user material model. That is actually like the most versatile and general model that we have in ATENA, and actually the user can describe the stress strain loss for the tensile and also compressive behavior of concrete. So we're talking about the models, but we need for those material models parameters, and those parameters we are getting from experiments. And when you perform direct tension experiments, because during this presentation or this webinar, we are focusing mainly on the tensile behavior of concrete. So we are talking about the tension testing. And when you perform the direct tension test, then you can use the parameters that you obtain from the experiment directly for your model. But mostly in the practice, when we want to find the tensile behavior of concrete, we usually perform bending testing. It's like the either 3-point bending tests or 4-point bending tests. And those results from experiments, they have to be modified to be used directly for the tensile stress strain law in material model. When we talk about modifying, it means doing basically inverse analysis, where you have to model your setup for bending testing, and then you compare the load displacement diagrams from experiment and from the model. Here you can see that there are like experimental results, and there is like initial model from ATENA when you are running your model, when you are simulating the experiment. On when you can see that there is a large difference, especially at the beginning of the diagram, you can change different parameters. Usually you're working mainly with the tensile strength and tension function with these sort of concretes. And manually you are changing the parameters and you are getting better as you are approaching the experimental result. So you can see like the first modification from the initial one that you're getting closer, but it might be time consuming and it also needs you to have probably experience with it or gain the experience with this inverse analysis. So therefore we developed the automatic procedure that is performed by our APIS module, APIS FRC, and that actually works with the multilinear function that is describing the tensile behavior of concrete, and this multilinear function is calibrated and it iterates until you're getting the results that you are satisfied with. So this APIS module was developed mainly for the 3-point and 4-point bending test. So when you want to work with it and you have the input, you are developing the input data that you need for it for the optimization of your material model, then you have to have results, experimental results from 3-point or 4-point bending tests. So the input data that you need is, first of all, you have to prepare the ATENA model in either our GID preprocessor, and then you have to specify the monitors for this model. It's like the first monitor that has to be there is load monitor, then the displacement monitor, of course, because you are working with LD diagrams, you are going to compare them, and then there has to be included also the max crack monitor. And then beside this model in ATENA, you need also the LD diagram that is from the actual experiment from the laboratory. So the optimization that is performed in APIS FRC is optimizing the tension function. The tension function, the initial one, you can find in your input file when you create the ATENA model. You create also the input file where are all the specifications of materials, of the loading of the supports, of your geometry, basically everything that is related to the model. And in material specification, you can find that there is like for your FRC material, there is tension soft hard function. And there is just the number of the function, so you can find directly how is defined the function. There are, it's as I mentioned before, it's multilinear function. So this one is made from 3 points, and here on the diagram you can see that there are like 3 points on the blue line. That is like the initial one. And as the optimization process is running, you can see that with the iterations, the tension function is changing and it's getting more and more points, so it's more specified. So when you run the iteration process, then there is like the preferences by the user how to stop this optimization, and it's either number of iterations that you specify or the target error. And another thing that you are taking from the input file is characteristic size of element that is used for crack width calculation, and that is not changing during the optimization. That is just one necessary thing to determine the strains from the correct width. I will mention it in here because I will go a little bit more into the optimization procedure. There is important assumption for the fitting process, and that is that the tensile strain in crack concrete is taken by fibers, and it's calculated from crack width and characteristic length of the element size, from characteristic element size that is given by this formula. And when you run the program, it works with initially selected points on the LD diagram that are used for the calibration of the tension function. And yeah, as I mentioned before, the tension function is specified also in here, that it's like residual strength with the fracture strain. And this tension function, that is the main thing that is calibrated during this iteration process. So I was talking also about 3 monitors that are necessary for the APIS FRC module to run. And now I go into specifics, why we need those, what is the procedure behind the optimization. So the first one is max crack monitor that is necessary to calibrate the tension function in X direction, because as you can see in the formula, the crack width is connected with the fracture strain. Therefore, we are talking about the calibration of the X direction of the tension function. Then there is another monitor, it's load monitor, that is necessary for the calculation of the Y direction, because we are talking again about the stresses about the load. So it's calibrating the tension function in Y direction, and also you can see that there is always like difference between the target load and the simulated load, so you can estimate the error that is there. The last monitor that is necessary is displacement monitor, and it's for the comparison of LD diagram that you get from the simulation, that you can compare it to LD diagram that you have from the experiment. So here is one of the examples when you run the APIS module, that you have the measured LD diagram from the experiment. This is the red one is the initial simulation of ATENA, and as you are iterating, you are optimizing the material model, you are getting closer to the experimental LD diagram. When you reach the point where you are satisfied with your material parameters, with the optimization, then you can apply it on different structures, more complicated ones, because this optimization works so far for those 3.4-point bending tests. So on the more complicated structures, you can apply it at the moment when you have like validated that material model. Yeah, this is one of the examples when you are running, when you have experimental results, and you can really tune it with the model. So, and now I would actually switch to the interface that we will try to run the program. And the easiest way for entering the APIS FRC module is to use ATENA Center, where you see the button for APIS FRC. So I will try to leave the presentation, and when you open the the APIS interface. There are two main parts where you are loading the first part. Where you are loading the model itself with an input file. There are specified like the geometry and everything regarding the model, and also there have to be included those 3 monitors that are necessary to run the optimization. And the second thing that you need to load is the LD diagram for your experiment. And there is a specification that it has to be file where are only 2 columns without any header. I have it in here just to show you that there are like just 2 columns and we are at the top, so there are no headers. And you have to, the first column is displacement and the second column is the load. And you have to be aware of which units you have in this load displacement diagram that they're corresponding to the ones that you have in your model, and also the signs the signs of the displacement or the reactions that they are the same. Then there are 2 things that you can adjust. The first one is the target error that you can increase or decrease. And then there is like maximum number of iterations that you want to run. When you have it set up, so I will load some example. Here you go to find your IMP file. And then you have to load that LD diagram from experiment. And then you can launch the optimizer. So first thing that you see here is the tension function, the one that is specified in your INP file, the initial one. I was showing it already before that usually if you have the default one, you have just 3 points on the function. And in this diagram, it's slightly modified the tension function. Because as you can see, the stresses are in the X direction and the strains or the crack width is the Y direction. It has its meaning because it will be better interconnected with other diagrams that we are going to load. So this is basically it's the tension function. It's just slightly flipped, and in this direction it's scaled a little bit, but the shape is the same. So we have like 3 combo boxes here, and we are selecting the respective monitor, the ones that we want. So in each combo box, we have a selection of all the monitors that are in our model. So for the displacement monitor, we choose the displacement. For the load monitor, the reaction. And for the max crack monitor, we choose max crack. Actually, all those monitors that are here, they will be named by you, so you will know what you are choosing when you are choosing it for the optimization. So it loaded more information at the moment we selected our combo boxes. So here you can see the experimental results, the measure diagram. Here the red curve shows the LD diagram for the first simulation with the initial tension function. And at the bottom part, there is diagram that connects the maximum crack width with the displacement. And I will get to this part a little bit later. So maybe we can start to run it because it will take some time to do the calculation. So when you start to run it, it runs on the background, and you can actually check that it's running in the folder of the model that you chose to optimize. So I chose this model. And when I go to ATENA calculation, I can already see that the first iteration is running. So the first iteration is running. There are visible some steps of the calculation that is already started. And this simulation that is running on the background with ATENA console at the moment, that started with the INP file that was already modified with different tension function that should be closer to our solution. So when I open this INP file and I scroll down to our tension function, it's actually the first one in here, the tension function for our user material. You can see that there are already more points on this multilinear function, not just 3 like on the initial one, but there are more points at the moment. And actually with this tension function, the simulation is running at the moment. And when the simulation is done, you can see that we have more steps already. When the simulation is done, the LD diagram will be drawn in this part. You will see also the tension function in this part, and this tension function, the diagram will be redrawn. So I would maybe show you a little bit more, because here are the lines. Wait a moment, I will just switch it. Yes. So in this diagram, I wanted to just point out the procedure of the optimization in APIS, and it shows you why we need those monitors that are specified there. So the first one where we are starting with the optimization basically is that maximum crack width. And I will change the better marker. So we are starting with the crack width. You can see that on this diagram, the crack width corresponds to the crack width on this diagram, that it's the same scale, the same values. And basically those two are interconnected then. So you can go from the crack width to calibrate the tension function when we were talking about it, that it calibrates in X directions, because we are talking about the stress strain diagram basically, and the strain and also the crack width is in here. So this is like calibrating the tension function in X direction. When you know where you are actually on the stress strain diagram in the X direction, then you can calculate also the Y direction, which gives you the residual strength. And that is something that you are getting from these values at the same point. That's why you also see that there is like displacement axis that is corresponding to displacement axis in here. And so you calibrated your tension function in X direction based on the crack width, and then you go to the low displacement diagram and you are calibrating it in the Y direction based on the target load and the load that is given in the simulation with the simulation. And yeah, so based on those values and the previous iteration, you are getting the Y direction, like the stress, residual stress direction of the tension function. Yeah, because the simulation that is running on the background, it will take some time because it has more steps. I can also show you some other simulation that has already more results, more iterations that were done. You can see that there are already 8 iterations. So I will load the model, and this is important question because it asks you whether you want to resume with your calculation, because it found already that you have 8 iterations calculated. So if you don't want to delete those iterations that are already calculated, you have to press to no. And it already knows the path to your LD diagram because it was already calculating it. And when you launch it, you can see already all those previous iterations that were calculated. So here you can see more LD diagrams as the iterations were getting closer to the experiment solution. In this part, there are more tangent functions, like this is the initial one, and then you have always like specified which iteration number is another function. Yeah. So this is the one that is running now. We still don't have the result. It will take some time because it's running the model. I just wanted to point out this part of the interface, because right now, when I started to run the simulation, it will run only the first iteration because I didn't increase the number of iterations here. So after the first iteration, it will stop, and you manually have to run it again, and it will run another iteration, unless you increase the number of iterations that should be run consequently. And it might be handy, especially when you want to suggest the next iteration, when you want to change it manually with this. So when it is not running, it's possible. Oh, so we got the result. Perfect. So here you can suggest the next iteration and run the fitter again. So now you can see that we got LD diagram for the first iteration. Okay. So there is one more thing that I wanted to show you, because recently my colleague Jan Červenka with Ulvis Skandins, they were working on a paper that is discussing the blind competition of shear beam behavior that was tested on fiber reinforced concrete T-beam. And Jan Červenka, he's from our company, of course, and then there is Ulvis Skandins that is from Latvia University of Life Sciences and Technologies. And they were studying this blind competition test because here you can see how the setup of the test for the T-beam looks like, what is like the reinforcement. And all the competitors, they got the results from experimental testing of FRC, of the fiber reinforced concrete. And those experimental results were from the 3-point bending test with the notch. And here you can see that through the inverse analysis in ATENA, we got the proper material model, and then we were running the calculation, the simulation of the T-beam. But even though the material model was fitted very well, you can see that the response for the whole structure and the prediction from our company was overestimate of the actual experiment. So in this paper that is actually it's still in the review process. It was not published yet, but it will also hopefully be soon published. So you can have a closer look on this, because it's very interesting. It shows that there this is result envelope from all the competitors. Here you can see the experimental average, and our prediction is somewhere in this area, like most of the cases actually. And you can see that most of it was overestimate for the actual experiment of T-beam. So they were running, the authors of this paper, they were running the parametric analysis. They were considering different parameters for the material model to see why there was such an overestimate. And they actually found out interesting thing, that when you are fitting, this is like the material model, and when you are fitting to the mean value of the experimental results, because this is like upper bound for the experimental results, and this is lower bound for experimental results. So when you are fitting it to the mean value, you are getting the overestimate. And we are talking about the 3-point bending test with the notch. But when they started to fit to the lower bound of material testing, they were getting much closer to the experimental results of T-beam. And also the crack pattern and the failure mode was getting really got to the point how it collapsed the T-beam. So they pointed out two things that they found out during this parametric analysis. And it shows actually that standard 3-point bending test on prisms with notch, that they tend to overestimate the material. It's because you're definitely defining the point where the prisms during the tests are going to collapse. But when it comes to the 4-point bending test, you have the zone where during the test, the worst area where the material is not strong enough is going to collapse as first one. So that's why 4-point bending tests might be a better solution. Otherwise, in case of you have just 3-point bending test, it's better to tend to the lower bound of the testing. And another thing that was probably playing a big role was also orientation of the fibers, because the casting of fiber concrete was performed from different directions when it comes to the T-beam or to the prism for the experimental test of the material. So it was not matching. Yeah. Well, so we are getting to the part where you can find also some more informations about either in general the material models for FRC or the APIS module. And again, you can find our documentation easily through the ATENA Center. And the 3 main manuals that I would recommend is the first one is directly manual for APIS users. Then there is ATENA theory that describes the FRC material models in general. And then there is also a very good manual for FRC material. It's tutorial with FRC material, and it goes through the inverse analysis step by step. So you can see there which parameters you can change and which parameters are influencing what during this inverse analysis of FRC materials. So that is very detailed and very nicely prepared. Okay, so maybe before I open the questions, there is one more thing that I wanted to mention, because we found out that in the latest version of the APIS module is a bug that will that will stop you from running, which is in the path that leads to your INP file. So in case of you want to run the APIS module at the moment from the installation, and you have the INP file somewhere in your computer, when you are checking the path, I maybe try to show you that you know directly what I'm talking about. So when we go to the INP file here, you can see the path. And when in this path there is no there is no space in either of the folder names, then it should be fine. But in case of there is a space in the name, like for example in here or so in here, then it will not run. So that is the bug that is already repaired, but it's not in the installation at the moment. So that is maybe one thing that you know why it's not running. And in any case, we are on hotline if you want to ask some questions. So I want to thank you very much for your attention, and I will have a look in the chat. And in case of some of you want to talk, of course, you can talk at the moment. So I have seen that somebody raised the hand, so maybe you can switch on the microphone and you can ask the question.
Yes, hello. Thank you for this very useful webinar. Just let me ask you, I'm planning to model FRC with plastic fiber, which is PET fiber. Mm-hmm. So I was wondering if the shear stiffening, the crack shear stiffening, are we apply the retention that according to Kepler 2000 and Colmar, or is there any other way to model the shear retention? This is my question.
Oh, Jan, are you there? I guess that
Yes, I'm here.
Maybe I need the help with these questions.
Yes, hello everybody. I think the question was about the shear retention factor, yes?
Yeah.
So maybe Michaela, if you can open Git. Do you have a Git there? And maybe open this file that we are working with. Some file with fiber reinforced concrete. I don't know if there's a Git file. So yeah, there is a Git file. Okay.
Well.
Yeah, and if you open the menu, if you now open the material model, the user material model, the dialog for the user material. Yes. So if you see the laws that you can define is the tensile. So if you go to the tensile, so you can define the tension, the graph. That's what Michaela was talking about now. Yes, this APIS FRC mainly helps you to define this stress strain diagram. Yes, this diagram. But your question was about the shear diagram, which is on the shear tab. If you click on that. So there you have two graphs that you can define, and one of them is basically this shear stiffness function, which is a function G divided by GC, which is like the shear stiffness divided by the original shear stiffness, which is basically the shear retention factor. Yes?
Okay.
And this is a very good point. What we are mentioning is that currently the law that is there as default is basically the Kolmar's law. That was your question about, I think, no?
Yeah. I mean, is there any more advanced way to model the shear?
Yes. Actually, what we normally do is maybe switch to the standard ATENA cementitious 2 model.
Okay.
So in the standard cementitious 2 model, if you go to Tensile tab, there is a shear factor, yes?
Mm-hmm.
So normally how we work is with the new ATENA model, we don't use the Kolmar law. What we use is that we directly determine the stiffness of cracked concrete in normal direction as the unloading branch, yes? If you see this crack opening law, and if you are somewhere on the softening branch, you can always find out what is the unloading, assuming unloading to the origin, yes? Or you can assume some irreversible crack opening, and then that's why we use this unloading factor. So if you have the standard value of the unloading factor, which is I don't know, 1 or 0 now, I think it's 0, standard way. Oh, 1, I'm sorry, I think it's 1 standard way. Oh, click on it, I'm sorry, I forgot now.
Which one, sorry?
Activate unloading factor. Okay, so normally by default it is 0, meaning unloading to the origin. So from this unloading branch, you can determine what is the cracking stiffness. And then we multiply this by this shear factor, and this is what we use for shear. So this is, let's say, a little bit different law, which is related not to some arbitrary law, empirical law like the Kolmar's rule, but it somehow is related to the stiffness of cracked concrete. So normally in ATENA, we recommend to use this approach that we use this shear factor. By default, it is 20, and we use it to calculate the shear stiffness as directly related to the normal stiffness. I don't know if you are following me.
Yeah, sure. And
so now I'm sorry.
Yeah.
So now, if I let me complete, you can extend it and use the same approach. So normally, what is best for the fiber reinforced concrete, if you define your G over GC function such that it corresponds to this approach.
Yeah.
Yes, because you know your softening diagram intention for the fiber reinforced concrete. Out of that, you can you know what is always the unloading at each point. You can multiply by 20. And then you need to manipulate it a little bit, and then you can use it as this G over GC.
Okay. Thank you.
Yeah. So this is what and actually in this paper that we are just about to publish, maybe once we publish it, if you send me your email, I will send it to you. All this formula is written there, yes? So you can use the formula directly from that paper. And we will also extend the manuals, because right now this formula, how to determine this G over GC, considering the shear factor, it is not there. You have to, let's say, derive it by yourself. And maybe even we will automatically add it to the model. This is, let's say, our latest finding. So, so we will extend the program and the documentation hopefully in the near future.
Thank you so much.
And there are some other questions I see here. Gunz, well, there was a question about the user material. So there is, in the documentation, there is a manual how to program your own user material in ATENA. And then there was a question whether we can use this APIS module for other user-defined diagrams. Definitely, yes, definitely. You could even use it for other structures, yes. But it's a question whether this algorithm that is there will work. But we have not yet done it, but we are also planning to use it for other structures, but we have not done that. But I think it should work. If the structure is a beam, yes, or and if you can relate, if your, let's say, the structural behavior is very much dependent or controlled by the tensor softening diagram, then you can use it for other problems as well. And then there was a question from Kunze. We were speaking about a short fiber reinforced, classically steel reinforced girder. For which fiber types is the model applicable? Because this makes difference. Steel, carbon, polymer, etc. Well, that's for different types or shapes of softening diagram, it is definitely applicable. So that means the same approach, the APIS module, or also this manual approach described in this tutorial, this can be used for other fiber types. In this sense, it is general. So you can use it for glass fiber, polymer fiber. This should not be a problem. Yeah, so maybe, Michaela, back to you. But there are no. There are some more questions. Yes.
Yeah, I just noticed that there is also a question how to insert own material model in ATENA. That is actually in the GID when we were talking about the user. There is this tensile tension function, and you can specify it in here. This is just the initial one that is there, but you can always start with other function that you define in here, and it is the same for compression or for shear. And I also wanted to show you something that I forgot, that actually when you want to use some iteration that you are satisfied with, that you always go to the INP file. You find the function. This is not the INP file. This is INP file. You go to see the tension function, the latest one that is in here, and either you can copy this function to another INP file that you are using for another structure, or you can type these numbers to the GID interface where I was at the moment in here. You can type it in here, and then you are using the optimized model. There is also a question about future plans of APIS. Yeah, this is like launching version sort of. So of course there are future plans that it will be more user defined. That you can define, for example, the points where you wanna check the function, because you can see those points that are automatically selected, for example, in here, that they're like with these dashed lines. And sometimes it can happen that those points are not selected properly, that they are not covering like certain curvature that might be on the diagram, especially at the beginnings in here. So that is something that should be also like that user can change it. One of the things. Module is identification of other types of user-defined diagrams. I am not certain. We are just focusing on the tension function at the moment. I'm not sure if I covered the questions.
There is one more question by Stanislav Aidarov. Should the FCMOD relationship be transformed analytically to F displacement 1 in case of dealing with 3-point bending theme? 3-point bending. I'm not sure what you mean because okay, I see. Yes, you need to have both because this program needs to have the F displacement relationship. Yes, so technically you should have both. Yes, when the program is run. Actually, yeah, this is a good question. I'm not sure now how to deal with that because you are right that in many cases you have this FCMOD rather than F displacement relationship, and you may not have it easily from your from your let's say from the experimentalist, yes. But on the other hand, it doesn't matter, yes. So this horizontal axis, this displacement can be anything. So it is just important. You can have this diagram, the reaction versus displacement. It can be reaction versus crack opening. So you could, strictly speaking, you have the same. You can use the same approach. Just replace this monitor with the monitor for the this displacement monitor with a monitor which would correspond to the crack opening displacement, and I think it should work the same. Of course, you will have then the crack opening on both axes here at this bottom graph. But that should not matter. Actually, in this analysis, in this experiment, just for some clarification, we monitor the max crack opening. We do not monitor the notch opening, yeah? So this crack mouth opening, which normally you get from the experiment. But it should not be a big difference, because the maximum crack opening is usually at the bottom. Okay, I think we don't have any more questions. And there were some requests for the paper. Unfortunately, we cannot send it right now because it is not yet published. But once it is published, once the review is finished, we can send it to you. Okay, so maybe back to you, Michaela. You can probably
wrap it up. So thank you very much for your attention, for your questions, and I hope it will be useful for you.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.